very often need to define directions in planes in a lattice or a crystal. So, for which a set of 3 indices are used, which are called as Miller indices. So, first let us consider directions and see how we can obtain a set of 3 indices to obtain a direction. So, let us consider an arbitrary unit cell. So, this is my unit cell, and let us take a specific direction here. So, let us take one of the corners of the unit cell and take the other corner of the unit cell. I join that to define a direction. Let us say, let me call this as OA. So, this is a vector. Basically, we are essentially direction means that we are trying to define a vector. Now, for a vector, we need 3 components in 3-dimensional space. In 2 dimensions, we would require only 2 components. And my standard, this is my A axis, B axis and C axis of the unit cell. So, OA, the 3 components would be along A, there will be some component, along B there will be another component, and along C there will be a third component. Now, along the A axis, you can see that actually if I look at the absolute magnitude of the component, then along A I have a component of the magnitude A, along B I will have a component B, and along C I will have magnitude of component C, which is nothing but the magnitude of the edges of the unit cell. But what we do is we make use of fractional coordinates, so that we do not have to specify A, B and C, because A, B, C are specified when you specify a crystal. So, we consider A to be 1 unit, B to be 1 unit and C to be 1 unit, and therefore, I can simply write the components as for this vector OA as 1, 1, 1. So, now there are 3 components, and therefore, directly the Miller indices for this direction would become simply 1, 1, 1, and conventionally that is put inside a square bracket. So, therefore, the direction OA has Miller indices 1, 1, 1 enclosed in square brackets. Let us take another example. Let us take this direction OB. Now, this direction OB or this vector OB is in the plane AB itself, and very clearly the 3 components for this would be 1 unit along A, 1 unit along B and 0 units along C. Therefore, the components are 1, 1, 0, the 3 components for this vector. Hence, the Miller indices for this simply becomes 1, 1, 0. Let us take yet another example, and let me take an example where this particular direction, this vector, which intersects the edge halfway in the middle. So, I will just write half there to show that this vector is intersecting the edge at the middle point of the edge. So, what are the 3 components for, let me call this as OC. So, for OC, I have 1 along A, 1 along B and 0 along C. Hence, the Miller indices becomes 1, 1, 0 again enclosed in square brackets. Now, let us try to take 1 or 2 more examples. And incidentally, do not take this as a cubic cell, it can be any of the unit cells in the Bravais lattice. Let me take a vector like this. Now, this vector is intersecting the top face at the midpoint. So, how do I now define the components for this? So, for this I need to shift the origin. So, let me call this vector as, let us say, DE. So, I shift the origin to point D. So, we will notice that what are the three components in this case? Well, it goes halfway along A in the negative direction. So, therefore, along A, so it is basically A by 2. So, I am removing the A and leaving the fractional coordinate. So, it is minus half. Along B, it is plus half, and along C, it is 1. So, let us take this. What do? I remove the fractions out of this. So, by removing the fractions, what I can do is I can simply multiply all the components by 2. So, that does not change the direction, it only changes the magnitude, and therefore, the indices should be minus 1, 1, and 2 into 1 will give me 2. This gives me the indices, and this is a conventional way of writing a negative number by putting a bar on top. So, it is bar 1, 1, 2. Now, let me come back to the previous case where I had actually made a small mistake. Come to the vector OC. In OC, along A it is 1, along B it is half. Therefore, the components are 1, half and 0. Again, to remove the fraction, I multiply this by 2 and the direction becomes 2, 1, 0. So, this is a very simple idea of defining a direction using 3 indices in crystal space or in lattice space. Now, coming to some specific unit cells. So, suppose I take a cubic unit cell. And this time I am taking a cubic cell as defined in the Bravais lattice, which is A equals B equals C. Let me consider first a direction like this. Its Miller indices clearly, along A it is 1, along B it is 0, along C it is 0, and therefore, the Miller indices becomes 1, 0, 0. So, this is let me call this as the vector OA. Let me call a second vector OB. So, this is OA. OB clearly would be, Miller indices would be 0, 1, 0, as it has 0 component along A, 0 component along C, and 1 component of unity along B. Similarly, if I define a vector OC, its Miller indices are going to be 0, 0, 1. Similarly, I can also define negative direction. So, instead of OA, I can say, let us say AO. Then what happens? I simply negate all the indices to show a opposite direction. AO would become bar 1, 0, 0. So, now minus 1 along A. Vector BO, again opposite of OB, is 0, bar 1, 0. Direction CO, opposite of OC, would be 0, 0, bar 1. Now, all of this, since this is a cubic cell, all of these directions, if we notice, suppose it is drawn in a lattice, with lattice points at the corners only. So, let us say primitive cubic. Then the direction along OA, the lattice points are going to be spaced with a distance of A, equally spaced with a distance of A. Along OB, since it is a cubic cell, again the spacing would be A. Similarly, along OC, the spacing of lattice points along that direction would be the same as for OA as well as OB. Therefore, we can put all of these 6 directions that we have here into a form what we call as symmetry equivalent directions. And they can be represented by three indices being put inside what are called as angular or triangular brackets, indicating that we are not just taking one particular direction, but all the symmetry equivalent directions that we have. So, all the 6 directions are defined by this 3 indices put under triangular brackets. So, these brackets are very important when we talk about Miller indices for directions as well as planes. So, we have to use specific brackets so that we are clear whether we are talking about a specific direction or we are talking about symmetry equivalent directions, which is also known as family of directions. Let us take another example. Let us say this is OD. Now, OD we have already seen that its Miller indices is going to be 110. Now, I can define many other directions which are symmetry equivalent to this cubic cell. Let us say this one. If I look at the Miller indices for this, I need to take the origin at point A, then there will be a -1 component along A, +1 component along B and a 0 component along C. So, therefore, the Miller indices for this direction would become bar 1, 1, 0. Take a third example. If I take this as the direction AC, its Miller indices would be, now this time it is -1 along A, 0 along B and 1 along C, and therefore, the indices becomes bar 1, 0, 1 and so on. You can clearly see that I can define similar directions on the third plane as well, third cube face plane. Like that, if I want to indicate now symmetry equivalent directions, they will be represented by the 3 indices 1, 1, 0 enclosed in triangular brackets. So, what are the various directions? So, I can simply permute this and write all the symmetry equivalent directions. So, 1, 1, 0, I can write 1, 0, 1, 0, 1, 1 and one can write the negative directions as well. Then there are other directions like bar 1, 1, 0. So, bar 1, 1, 0, bar 1, 0, 1, 0 bar 1, 1 and one can write the negative of all these 3 directions. So, 1 bar 1, 0, 1, 0 bar 1, 0, 1 bar 1 and so on. So, I have written all the possible symmetry equivalent directions along the phase diagonals. Now, sometimes we may want to give an absolute magnitude for a particular direction, because these are indices in which we are not bothered about the magnitude of the vector, we are only bothered about the direction of that vector. So, if I want to specifically write a specific magnitude, so whenever we write down the indices for the direction, we always need to put down which is my vector A of the unit cell, vector B of the unit cell, or the vector C of the unit cell. If I do not specify that, then my directions would become meaningless, because I do not have a reference. So, let us take a specific direction like OA. Now, A is the midpoint of phase. So, of course, if I just want to write down the Miller indices for this, I will say that it is half component along A, half component along B, and 0 component along C, and I can simply multiply this by 2 to remove the fractions, and I will get the direction 1 1 0. But now I want to write specific magnitude. We know what is the magnitude for this. Since this is let us say this is a cubic unit cell. So, A equals B equals C. So, if I have to write the specific magnitude, I know what is the specific magnitude of this. This is half the length of the phase diagonal. And what is the full length of the phase diagonal? So, is A root 2. It is half, so therefore, I divide by 2, and I will get basically the magnitude A upon square root 2. Now, in order to write this specific vector with specific magnitude OA, I can write in the following form: A upon 2 1 1 0. So, I have the Miller indices 1 1 0, and then whatever magnitude I get from the 1 1 0, I multiply this by A by 2 to get me the specific magnitude. So, as we can see, if I have to get the specific magnitude, say I will call it OA without the bar, then this would be A by 2 times 1 square plus 1 square plus 0 square to power half, and this gives me A root 2 upon 2 or A upon root 2. So, by this method I can also give an absolute direction.